Hi everyone, I'm Dan Jing. Today our group will present a paper titled Belief Projection-Based Reinforcement Learning for Environment with Delay Feedback with S-star ranking. Our group member including Lin Chunyi, Ho Jingyun, Dan Yanvi, and me, Dan Yijing. This is the table of content of our slide. And now we will go to background. The reinforcement learning is widely used in robotic control decision making and real-world continuous control tasks. The reinforcement learning allows agents to handle high-dimensional and continuous problems and achieve superhuman performance, and is also increasingly applied in real-world control tasks. Normally, environment is modeled as a macro decision process, meaning that the next step only depends on the current state and action. This is the example of the application. However, in real-world situation, there is often the feedback delay due to sensor or actuator latency caused by hardware issue. Large quantity data like high resolution images and network communication delay as the agent is located far from the controller. Consequently, the standard macro decision process make assumption fail because it cannot make decision based on the current state but is outdated state. This will make the poor learning and performance. Hence, belief projection-based Q-learning is proposed to overcome a constant delay environment. Now we will go to motivation. Why propose a new algorithm? This is because existing methods all have fundamental drawbacks. The first method is called complete information method or augmented state method. It can transform the delay environment into the standard macro decision process problem. But when the delay state increases, the state space grows exponentially. This method, learning slows down, memory usage increases, and efficiency drops. The second method is called state estimation method or models-based approach. It does not need to expand the state space, but it relies heavily on an accurate environment model. When it is in complex or stochastic environment, the model error accumulate rapidly and making training unstable and difficult, especially with long delay. And the closer words to the proposed algorithm is expectation maximization Q-learning EMQL, but it only works for discrete state action space and it still suffers from dynamic model error. Hence, this research is to overcome both drawbacks. One is avoid model dependency so it can be model free, and second one is to avoid dimensionality explosion so there is no curse of dimensionality. Hence, this is why the proposed algorithm was born. Now I will pass to Jingyu for challenge and methodology part.
Good afternoon, everyone. I'm the third presenter called Kao Jingyun, and I will explain how the proposed BPL method solve the challenge introduced earlier by Yijing. And there's many methodology flow, but I will only explain the important part of the methodology and what is the innovation that solve the challenges. So let's go through for the first solution. For the first challenge, the first challenge is called the argument state methods. So because of the argumented state-based QL, it has the problem like it got the exponential growth problem, and because the delay increase. So that's why I suggest with the people suggest a new method is called beta Q functions, and this is how to stable the training even when the delay is large, and also keep creating network always stay small. And also the second one is the model-based approach. And this is solved by using a technique called fully model free learning with the delay replay alignment. So for the previous transition model, it will keep accumulating the error over the time until the learning accuracy become low. So the new requires a transition safe in replay buffer is implement in this BBQL. So this approach is this repair buffer approach is allow the BBQL to store the actual transition directly, meaning it always learns from your state rather than predicted one. So BBQL completely avoid the compounding model errors even when the delay is low. And the last solution for the challenge tree is the EMQL only works from this space, because the major problem of this paper is about like how to solve the delay problem. So usually the delay problem will happen when the element is in a continuous state. So to solve this problem, the all one the formula, this one have to be replaced by the new one, the new solutions. So the new one is we call as the belief projection formula. It is one of the important formula and what we want to focus in this whole methodology. So it can help to work from the continuous state, stress state mutual call, and also it can work from continuous actions. Yeah. And also these expressions can help BPQL approximate the expectation using sample transition from the repair memory. So the repair memory is similar as the replay buffer, as shown here. So it can keep the previous action state and the current state and actions except the future one. So combining this and with the belief projection formula, the model BBQLs can learn in the continuous state and continuous action. So how it works, how it experiment will be explained by Jamie later. So that's all for my part. Thank you.
I'm Yevi, so now let's continue to the part of dataset. Datasets are mainly focused on mutual core, and there are some from OpenAI Gym. These are the environments that we will be mainly focused on. And these are the setups of the experiments. The base reinforcement learning algorithm is the soft actor critic. There are three of them, which is the normal one, the delay one, the augmented one. The delay one is the model-based approach, and the augmented one is the augmented state method. And today we are focused on this main algorithm, which is belief projection based Q learning. Okay, for each task, there are 1 million of time steps, which is then repeated with 5 different random states. The environment are then set to 3, 6, and 9 delay time steps. This is one of the result of a single environment from major core. As we can see, the delay time steps are 3, 6, and 9. The red line state the BBQL algorithm, which we are mainly focused on. As we can see, for small delay time steps, all algorithms perform well except normal SSE. And as the increasing of the delay time steps, BBQL outperforms all the algorithms, which it has a stable and better performance. This is the table of average return, which is the score in all environment from mutual core. As we can see from the yellow highlighted score, BBQL still outperform in most situations with high score. Even in the large delay environment, it is still perform well among all the other algorithms, as well as the result in OpenAI Engine.
To talk about the insight and the significance about our group after reading these wonderful papers. After reading these wonderful papers, we found that actually the authors is very, very smart. Instead of keeping a huge memory of delay actions, the author simply estimate where the agent probably is right now. It's like almost guessing your location when your GPS is lagging. This make the learning much simple and faster. But the downside is that the delay must be fixed. The real world delay are messy, sometimes fast, sometimes slow, so the method might struggle outside simulation. And because the algorithm learn belief from data, a real robot might need a lots of practice and a lots of data before performing well. Next, we talk about the research significance about these papers. So why is this book is very important? Because delay happen everywhere in the real life. In robot, drone, sensor, camera, even network control machines also have delay. If RL can't handle delay, it can't be applied in the real world system. This paper showed practical ways to handle delay without exploiting the state space and without needing a perfect world model. This make a promise step towards RL that actually works in the real world. Next, some future research directions. A big direction is handling the random and unpredictable delays, which what's happened in the real communications and the hardware settings. Another direction is testing the BPQL on real robots, not just on the simulations. And I think combining belief, and our group thinks that combining belief projections with model-based RL could reduce the data needed and make learning more faster. So in conclusion, this is a very, very wonderful and insight travel ideas that simplify the ideas. The delay reinforcement learnings has a strong potential for real applications, and it still needs some improvement for realistic delay, and it also provides several existing paths for the future research. So that's all for our team. Thank you very much.